This is a video walkthrough for the Unit 8 review. For number 1 and 2, we're asked to find the result using polynomial long division. Quick note, for these two exercises, the divisor is not in a form where you may use synthetic division, so synthetic division will not work for these. For number 1, we're going to set up the division and put 0 placeholders where appropriate. So 9x cubed plus 0x squared minus 7x plus 5. So first step is first term divided by first term. 9x cubed divided by 3x is 3x squared. Next step is to multiply 3x squared by the entire divisor. 3x squared times 3x is 9x cubed. 3x squared times negative 2 is negative 6x squared. Next, we're going to change the signs on the multiplication that we just did. First term to negative, second term to positive, and add. And we get 6x squared minus 7x plus 5. You can just bring down all the terms if you wish. Next step is first term divided by first term, so 6x squared divided by 3x, and that result is positive 2x. Now take that 2x and multiply it by the entire divisor. 2x times 3x is 6x squared, and 2x times negative 2 is negative 4x. Next, we're going to change the signs of that multiplication that we just did, first term to negative, second term to positive, and then add. And that result will give us negative 3x plus 5. Next step is first term divided by first term, so negative 3x divided by 3x is negative 1, and multiply that negative 1 times the entire divisor. Negative 1 times 3x is negative 3x, and negative 1 times negative 2 is positive 2. Next, we're going to change the sign of the multiplication that we just performed, first term to positive, and second term to negative, and then add, and that result will give us positive 3 as a remainder. It is not possible to divide 3 by 3x, so we're just going to write our answer. The quotient is 3x squared plus 2x minus 1, and then plus the remainder over the divisor, which is 3x minus 2. For number 2, I'm going to write my divisor, x squared plus 3, divided into the dividend, x to the fourth plus 2x cubed plus 8x squared plus 8x plus 14. No need for 0 placeholders in the dividend. First step is to divide first term by first term. X to the fourth divided by x squared is x squared. And then multiply that x squared times the entire divisor. X squared times x squared is x to the fourth. X squared times 3 is 3x squared. Be careful to place the 3x squared underneath its like term in the dividend. Now we're going to change the signs of both of those terms and add, and we get 2x cubed plus 5x squared plus 8x plus 14. I'm just going to bring down all the terms. Next step is to divide first term by first term. So 2x cubed divided by x squared is 2x. So plus 2x is the next term of the quotient. Next, we need to multiply 2x by the entire divisor. 2x times x squared is 2x cubed. 2x times 3x is 6x. Next, we're going to change the signs of those two terms, first term to negative and second term to negative. And then add, and we get 5x squared plus 2x plus 14. Next, we're going to divide first term by first term. So 5x squared divided by x squared is 5. So plus 5 is the next term in the quotient. Next, we're going to multiply 5 by the entire divisor. 5 times x squared is 5x squared. 5 times 3 is 15. Next, we're going to change the signs of the multiplication that we just performed. First term to negative, second term to negative, and then add. And the result is 2x minus 1. And that's our remainder, since 2x is not divisible by x squared. So the quotient is x squared plus 2x plus 5. And then we add plus the remainder, 2x minus 1, divided by the divisor, x squared plus 3. In 3 through 4, we're asked to find each function f of x or g of x. In standard form, that means multiplied out. So I'm just going to write what it says. When I take f of x and I divide it by 2x plus 7, the result is 3x squared minus x plus 1. And we're asked to find f of x. In order to do so, I'm just going to multiply both sides by 2x plus 7, so 3x squared minus x plus 1 divided by 2x plus 7. If you want to use a box to perform that multiplication, you can. 3x squared minus x plus 1 times 2x plus 7, that's 6x cubed minus 2x squared plus 2x plus 21x squared minus 7x plus 7. So, combining like terms, f of x is equal to 6x cubed plus 19x squared minus 5x plus 7. In number 4, I'm just going to write what the division says. When I take g of x and I divide it by x squared minus 5, the result is x plus 3 plus 4x plus 7 over x squared minus 5. When I multiply both sides by x squared minus 5, we get g of x is equal to x plus 3 times x squared minus 5 plus 4x plus 7. Multiplying the two binomials together, we get x cubed plus 3x squared minus 5x minus 15, and then adding that remainder on, we just need to combine like terms. X cubed plus 3x squared minus x minus 8. In 5 through 6, we're asked to perform synthetic division. In synthetic division, the box contains the 0 of the divisor. X plus 3 is equal to 0 when x is equal to negative 3. Next to it, place the coefficients of the dividend. 2x cubed minus 1x squared minus 17x plus 4. Skip a line, bring down the 2 times negative 3 is negative 6. Add that line, or add that column. Negative 7 times negative 3 is positive 21. Adding that column, we get positive 4. 4 times negative 3 is negative 12. Add that column, we get negative 7. Excuse me, negative 8. Now we need to write what this quotient means. That's 2x squared minus 7x plus 4 plus negative 8 divided by the divisor x plus 3. In number 6, the 0 of the divisor, which is 2, because x minus 2 is equal to 0 when x is 2, goes in the box. And then the coefficients of the dividend go next to it. 1x cubed plus 0x squared plus 0x minus 5. And then skip a line, bring down that 1, times 2 is 2, add that column, times 2 is 4, add that column, times 2 is 8, add that column. Here's our coefficients for the quotient, and there's the remainder. So the quotient is x squared plus 2x plus 4 plus the remainder of 3 divided by the divisor x minus 2. In number 7 through 8, we're asked to find synthetic division to find each function value. By the way, you can find each function value by doing the following, just substituting. But this is not what this question is asking you to do. It's asking you to utilize synthetic division. So we're going to divide by x minus a half, and the remainder will be equal to f of 1/2. So the coefficients of the dividend, or f of x, are 4x cubed, 0x squared, negative 5x, and 9. Now performing the division, bring down the 4. 4 times a half is 2. Add that column. 2 times a half is 1. Add that column. Negative 4 times a half is negative 2. Add that column, that's 7. So that means that f of 1/2 is equal to 7. In number 8, finding the remainder when dividing by x plus a third is the same as finding g of negative 1/3. So a negative 1/3 goes in the box. The coefficients of g of x go next to it. 3x cubed minus 5x squared plus 7x plus 1. Bring down the 3 times negative a third is negative 1. Add that column. Negative 6 times negative a third is 2. Add that column. 9 times negative a third is negative 3. Add that column. And so the remainder is the value that we are looking for. G of negative 1/3 is equal to negative 2. In 9 through 10, we're asked to consider a cubic function p of x with an unknown coefficient k. And we want to find the value of k such that each division has the specified remainder. So when I divide p of x by x minus 2, the remainder is 1. This is equivalent to writing p of 2 is equal to 1 by the remainder theorem. This is probably the easiest way to work it rather than doing a division. So p of 2 is 2 cubed plus k times 2 squared minus 3 times 2 plus 7. 2 cubed is 8, 2 squared is 4, 3 times 2 is 6, and so p of 2 simplifies to 4k plus 9. If p of 2 is 1, then 4k plus 9 must equal 1, and subtracting 9 and dividing by 4, we get k equal to negative 2. For number 10, by the remainder theorem, p of x divided by x plus 2 has a remainder of 29 is equivalent to writing p of negative 2 is equal to 29. So we're going to take our function p of x and replace x with negative 2. P of negative 2 is negative 2 cubed plus k times negative 2 squared minus 3 times negative 2 plus 7, which is negative 8 plus 4k plus 6 plus 7, or 4k plus 5. If the remainder is 29, then p of negative 2 is 29, so 4k plus 5 equals 29. Subtracting 5, 24 is 4k, and k is 6. In 11 through 12, we're asked to find the remainder of the division, but looking at the degree of the polynomials in question, it would be too cumbersome to actually do a division, so we're going to apply the remainder theorem. So if we want to find the remainder when f of x is dividing by x plus 1, what we actually want to find is f of the 0 of the divisor, which would be negative 1. So f of negative 1 is 2 times negative 1 to the 91st power, plus 5 times negative 1 to the 48th power, minus 3 times negative 1 plus 1. Negative 1 raised to an odd power is negative, and negative 1 raised to an even power is positive 1. Now we can perform our multiplications. Negative 2 plus 5 plus 3 plus 1. And f of negative 1 is equal to 7, so 7 is the remainder. In number 12, we're asked to find the remainder when g of x is divided by x minus 1. So that's equivalent to, by the remainder theorem, finding g of 1, which is the 0 of the divisor. So that would be 6 times 1 raised to the 37th power minus 4 times 1 raised to the 8th power plus 1 plus 7. And 1 raised to any power is 1. So 6 times 1 is 6. 4 times 1 is 4. And now we just need to add g of 1 is 10. So 10 is the remainder when we divide by x minus 1. In 13 through 14, we're deciding if x minus 2 is a factor of the given polynomial and justifying our answer using the remainder theorem. Factors divide evenly with a 0 remainder. So that means that we are looking for a 0 remainder, and if we're dividing by x minus 2, the value of the remainder is equivalent to h of 2. So h of 2 is equal to 2 to the 5th minus 25, and that's going to be 32 minus 25, which is equal to 7. Since h of 2 is equal to 7, and that is not 0, x minus 2 is not a factor. In 14, if we're trying to determine if x minus 2 is a factor, then we want to determine if we have a 0 remainder when we divide by x minus 2. So I'm going to find p of 2, which is 2 cubed plus 3 times 2 squared minus 9 times 2 minus 2. And that's 8 plus 3 times 4, which is 12, minus 9 times 2, which is 18, minus 2. And that would be 20 minus 20, which is 0. Since p of 2 is equal to 0, then x minus 2 is a factor, because we are looking for a 0 remainder. That means that something divides evenly without remainder. So what we're dividing is a factor. In 15 through 16, we're deciding if x plus 1 is a factor of the given polynomial and justifying the answer using the remainder theorem. So if we're finding the remainder when we divide by x plus 1, that's equivalent to finding f of negative 1. And f of negative 1 is negative 1 to the 72nd power plus 7 times negative 1 to the 9th power minus 2 times negative 1 to the 5th power plus 4. A negative number to an even power is positive. A negative number to an odd power is negative. And for the third term, negative number to an odd power is negative, but a negative times a negative is a positive. And so this gives us 1 minus 7, which is negative 6, plus 2 is negative 4, plus 4 is equal to 0. So if f of negative 1 equals 0, then x plus 1 is a factor. In 16, if we're deciding if x plus 1 is a factor, that's equivalent to finding g of negative 1 and finding the remainder that way. G of negative 1 is negative 1 cubed plus 5 times negative 1 plus 2. Negative 1 cubed is negative 1. 5 times negative 1 is negative 5 plus 2. So g of negative 1 is negative 6 plus 2, which is negative 4. And that is not 0. So x plus 1 is not a factor. In 17 through 20, p of x is a polynomial with integer coefficients. That's important because that means that any solutions that are either non-real or irrational must come in conjugate pairs. Some of the solutions are given, and we need to find the other solutions. That is to say, any conjugate pairs that exist, and then the least possible degree of p of x. So in 17, we have one non-real solution, and if we put this in a plus bi form, that's 0 plus 4i. The conjugate pair must also be a solution, so negative 4i will also be a solution. 3 is a rational number, so it will not have a conjugate pair. The square root of 2 is irrational, so the conjugate pair, negative square root of 2, must also be a solution. Now we have a total of 5 solutions that are given, so the least possible degree of p of x must be 5. In 18, there are 2 rational solutions. They will not have a conjugate pair solution. We have 1 irrational solution, so the conjugate pair must also be a solution. Now there are a total of 4 solutions given, so p of x must be at least degree 4. In number 19, we have a non-real solution, so the conjugate pair 3 plus I times the square root of 7 must also be a solution. The other given solution is a rational number. That's a fraction, something that can be expressed in fraction form, and so it will not have a conjugate pair. So there are a total of 3 solutions given, then p of x must be at least degree 3. In 20, we have a non-real solution, 2 plus 3i. 2 minus 3i must also be a solution, and an irrational solution, negative square root of 10, so positive square root of 10 must also be a solution. There are a total of 4 solutions given, so p of x must be at least degree 4. In 21 through 26, given 1 or more solutions or roots of a polynomial equation, find the complete solution set. This is degree 3, so if we are given 1 solution, we're expecting 2 more. So if negative 2 is a solution, that means that x plus 2 is a factor, and if x plus 2 is a factor, we can divide by it to find the other factor. You could use polynomial long division, but synthetic division would probably be easier. So we're going to divide by x plus 2, and we're dividing into 1x cubed plus 4x squared minus 11x minus 30, and bring down the 1 times negative 2 is negative 2. Adding that column, that's 2, times negative 2 is negative 4. Adding that column, that's negative 15, times negative 2 is positive 30, and we get a 0 remainder. Here's our quotient. That's the other factor, which I'm going to set equal to 0. And this particular polynomial does factor x plus 5, x minus 3. And so x plus 5 is equal to 0, or x minus 3 is equal to 0. So x is negative 5, or x is equal to 3. So complete solution set would be the given solution and the 2 solutions that we just found. In number 22, we have a 4th degree polynomial and 2 solutions given, so we need to find the remaining 2. So we're going to first divide by x minus 3 into 1x to the 4th minus 4x cubed minus 8x squared plus 23x plus 30. Bring down that 1 times 3 is 3. Adding that column, that's negative 1 times 3 is negative 3. Adding that column, that's negative 11 times 3 is negative 33. Adding that column, that's negative 10 times 3 is negative 30, and we get a 0 remainder. Now we're going to take this quotient and divide that quotient by x plus 2. Bring down the 1 times negative 2 is negative 2. Add that column, that's negative 3. Negative 3 times negative 2 is 6. Add that column, that's negative 5. Negative 5 times negative 2 is positive 10. Adding that column, we get 0. This is the remaining factor once we've divided out the factors that produce the solutions of 3 and negative 2. So we're going to take that and set that factor equal to 0. And this is perhaps best solved by the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared, which is 9, minus 4 times a times c. And that's all over 2 times a. So x is equal to 3 plus or minus, and inside the square root we have 9 plus 20, so 29 over 2. And that's not the complete solution set, that's only 2 of the solutions. So our complete solution set includes 3, negative 2, the given solutions, and 3 plus the square root of 29 over 2, and 3 minus the square root of 29 over 2. In 23, we have one given solution. If x equals 1 is a solution, then x minus 1 is a factor. So we can divide by x minus 1. into 1x cubed plus 9x squared plus 16x minus 26. Bring down the 1 times 1 is 1. Add that column, that's 10. 10 times 1 is 10. Add that column, that's 26. 26 times 1 is 26. Add that column, we get 0. So the remaining factor is x squared plus 10x plus 26. Set that equal to 0. And this is probably best solved by the complete the square strategy. So I'm going to subtract 26 from both sides. And then I'm going to draw a picture for complete the square. X squared, divide that middle term into two equal pieces, 5x and 5x. That suggests factors of x plus 5 and x plus 5. Completing the square, 5 times 5 is 25. And so we have x plus 5 squared is equal to negative 1. Taking the square root, x plus 5 is equal to positive or negative square root of negative 1, which is I. And adding negative 5 to both sides, negative 5 plus or minus I, are our two remaining solutions. But we want the complete solution set, so that would be 1, negative 5 plus I, and negative 5 minus I, for a total of 3 solutions. For number 24, we have a total of 4 solutions for this 4th degree polynomial equation, and we have a given solution 2i. That means that negative 2i, the conjugate pair, is also a solution. Rather than use synthetic division, where imaginary or irrational numbers are concerned, I'm going to suggest that we write the factors. So x minus 2i is one factor, and x plus 2i is another factor. And let's multiply those two factors together. That gives us x squared minus 4i squared, or x squared plus 4. In order to find the remaining factor, once these two factors are divided out, I'm going to use polynomial long division. So x squared plus 4 divided into x to the 4th minus 2x cubed plus 3x squared minus 8x minus 4. First step, first term divided by first term, x to the 4th divided by x squared is x squared. And then x squared times the entire divisor, that would be x to the 4th. X squared times x squared is x to the 4th, and 4 times x squared is 4x squared. Now I'm going to change the signs of the terms in the multiplication that we just did, both to negative, and add negative 2x cubed minus x squared minus 8x minus 4. I'm just going to bring down all the terms. Next step would be first term divided by first term. So negative 2x cubed divided by x squared is negative 2x. And now we need to multiply negative 2x by the entire divisor. Negative 2x times x squared is negative 2x cubed. Negative 2x times 4 is negative 8x. Now I'm going to change the signs of the multiplication that we just did, both terms to positive, and add. Now we get negative x squared minus 4. And we're going to divide once more, first term by first term. Negative x squared divided by x squared is negative 1. Now multiply negative 1 times the entire divisor. Negative 1 times x squared is negative x squared, and negative 1 times 4 is negative 4. Next, I'm going to change the signs of both of the terms in the multiplication we just performed, and add, which gives us a remainder of 0. So the quotient here produces the other factor that we are looking for, which is x squared minus 2x minus 1, which we can set equal to 0. And this is probably most easily solved by complete the square. So I'll add 1 to both sides, and then draw a picture for complete the square. X squared and then divide the middle term into two equal pieces, minus 1x and minus 1x, which suggests factors of x minus 1 and x minus 1. To complete the square, negative 1 times negative 1 is positive 1, so we'll add a 1 to both sides of the equation, and that gives us x minus 1 squared is equal to 2. Taking a square root, x minus 1 is positive or negative square root of 2. And adding 1 plus or minus 2 are the remaining two solutions. So we had the given solution 2i, its complex conjugate, negative 2i, and the two solutions that we just found for a complete solution set of plus or minus 2i and 1 plus or minus the square root of 2.